So let's welcome our second speaker, Marjan, and she will tell us about her work in music synthesis. Marjan, take it off.
Good afternoon, thanks for coming. My name is Marjan Rouhipour, I'm a master's student here, and I'm working under supervision of Dr. Tomaras. Today I want to talk about computer music. This is a multidisciplinary field. It's a combination of music, computing science, electrical engineering, mechanical engineering, and physics. So today I want just to give you a big idea of what we do in this field. If you consider electrical musical instrument as this chart, you have an interface. It can be something like a remote controller, like Wii controller, or a touchpad. Then we have some parameter like frequency, volume, duration. Those interfaces match to the parameter. So you might have a slider and by changing it, you can set the frequency or volume. Then we have a model of instruments, saxophone, guitar, piano, anything you can imagine. And then we have the sound. Now I want to talk about the interface. One of the first useful musical instrument, electrical musical instrument, was theremin. You may see it before. It has two antennas and it can control the pitch and frequency. Sorry, pitch and volume, just by distance between dance and this antenna. This instrument developed by Mr. Theremin in 1990, and this video shows Mr. Theremin who plays this instrument.
Электромузыкальный инструмент орган-бокс и мелодии достигает.
It's very difficult to play it, to master and playing this instrument, but it's possible. And people still use it in some concerts. Okay. So interfaces are very important in this field. People try to use computer and electrical music instrument in concert. This is a laptop orchestra developed by Perry Cook. And if you look at this, just watch this video. You can see there is a leader and just stand there, move hands, and all players just sitting there and move their finger. It's not a good interface. There is no interaction between players and audience. So you need more useful interfaces, but it's a huge work, actually, I can say. So now you watch better interfaces. Some of them are crazy. See, they have sensors on their hand, if you see. They have some kind of gloves, move their hands, and try to make some kind of sound or something like that. If you go forward. You see how they adjust the pitch, volume. By moving their head, you also have sensors. Sometimes motion detection helps. That's it. That's why interfaces are very important. But my work usually is in this part, modeling. We try to model the saxophone. If you have an interface, but you have a science behind it, how to produce, how to synthesize the sound. That's why we should know some sound synthesis techniques. These are most popular ones, like wavetable. There is a table of some wave with a specific frequency, and it's very popular. Additive synthesis is kind of different sinusoid, and you add them together, or subtractive. The one we used recently is physical modeling. Physical modeling is started by Julius Smith. The concept of physical modeling exists before, but he's the first person used physical modeling for synthesis of sound. So we use mathematical model to generate the waveform of sound. It's very efficient computationally and very easy to use. And it can be implemented by digital delay line. I will explain it later. So, physical modeling is based on standing waveguides. So, if you just blow in a tube, you generate some wave inside it. So, two kind of wave generate. The blue one is the right going, and green one is left going. And they sum together, they make this red one, which is a standing waveguide. That is what we call the harmonics. The first harmonic, the second harmonic. So here, we have another example. They are fixed at both ends, for example, like a string of a guitar. When you plug a string, this standing waveguide generated, it has two left and right going wave. In implementation, we have two delay lines. It's digital, so we have an array, just shift the value to the right or left. So for example, you plug it, the position is 1 here, then it starts to shift here. At the end, which is this notch here, it's multiplied by -1 in idle case, and comes down, it shifts again, and on the other side, it's again multiplied by -1. How we get the standing waveguide? We sum at each point. We can sum two of these indexes from left and right going array, and then we have the value of the standing wave. So we can have the sound at each point. Usually we need it at one end here or here, but we can do it, for example, here. It's not possible in real world, but that's one of the benefits of having the virtual model. We can get, okay, what's the sound like if we get the output from in the middle. So I want to measure how these instruments are different. For example, if I have a tube and it's open at both ends, so we have the harmonic like this. So the standing waveguides are different from in the previous slide. So if in case of clarinet, it's a closed open tube, so the harmonic is different. And for a guitar, it's a string fixed at both ends. That's why instrument sounds different. Both instruments play with frequency 440 Hertz, but we distinguish which one is flute, which one is piano. That is one reason they are different. We can from top to down, but it's not only one-way direction. We can go from down to top. That's my thesis focused on this direction. So we have the sound. We want to know, okay, what is exactly the model of saxophone? How we can produce that model? So we focus on the time and frequency domain extract picture. That's where we use machine learning techniques, and it can be useful in other fields like information retrieval. And we can also say, okay, which frequency can produce a specific sound. To conclude, I can say computer music is very useful to model traditional instruments. We need them. Why? Because we cannot carry lots of instruments with ourselves or storage it at home. We cannot learn to play all instruments. Composer really need those instruments, or we as ordinary people, we like to, make maybe a piece of music, I don't know. But we need those traditional instruments. And sometimes it's not possible to have a strange musical instrument, like a saxophone, which has, I don't know, 10 kilometers long, I don't know. It's very strange, but we may want to know how does it sound. So we need new musical instruments. For entertainment, we need this. As you see in the picture, for example, with V controller, we'll try to make new games. And for singing, it can be used also for the singing. Thank you very much. I'm here to answer your question. Thank you.
And we welcome question from the audience. Yes, Irfan.
How expensive was those interfaces?
Which one?
Like
Some of them are
in the head?
sensors. They design it electrical engineer. They are electrical engineers, so they design those interfaces.
So is it possible for us to pay it, or?
It depends. For example, you can buy B controller and write code for it and use it as a musical instrument. I think for interfaces, it's usually based on I don't know how you want to match those interfaces to model. That's more important. I don't know how much they cost.
And those interfaces are independent of the instrument, right? You can plug it to make the sound of guitar or saxophone with the same interface.
Actually, they have some software behind them, so they can just use a laptop and just keyboard, but they prefer to have more interactive interfaces. That's why they use, for example, with shaking head, for example, they try to set the pitch or vibration or glassing or something.
So, I also have a question regarding your research particular. So, were you able to create a model using the sounds, or like you said, you're going up the stack?
Here.
Yes.
Okay.
So, what about input parameters?
If we have the model, we can design an interface, but we have a sound. For example, in my thesis, I have a saxophone sound. I want to know what is exactly the saxophone is. For example, it has a bell, and it's not defined well in theory. So we need to design a filter. If you go to here, I mentioned it's an ideal case, you have -1 here. So if you consider that's a saxophone, just the tube or the cone part of it, and we know exactly the length, which is not possible sometimes because the airspeed is different, so we have the different samples number. So we should know what should we put here as a filter. Is it a low pass filter? If we have a fractional delay here, for example, we put an all pass filter. What is this all pass filter? We should know those things, and that's our job. We try to get impulse response of instrument and then work on them, extract features, and to understand what it is.
Okay. So let's thank Marjan for this wonderful talk. And we have our next speaker, who is Jeremy. We're going back to the origins, which is medical imaging. 1 second.